So yeah, my name's Dan Bailey. I'm here on behalf of Double Negative. And I'm going to roughly kind of split this talk into sort of three parts, give you a bit of an idea of the kind of problems we're trying to solve and the context to which we're trying to find a solution. And then I'm going to talk about the solution that we've come up with and the compiler and language that we've developed to try and solve that problem. And then finally talk a little bit about the LLVM PTX backend that we're using. So first of all, a bit of an introduction to the company that I work for. I work for a company called Double Negative. Our main offices are just down the road here in London. We also have a studio in Singapore as well. And we've got quite a large and sort of steadily growing R&D team, which is just over 50 people at the moment. So first of all, the kind of class of problems that we're trying to solve here, like a lot of the kind of problems that we are tackling in R&D tend to be around sort of simulation problems where we're trying to solve things to produce, to put onto a presentation, put onto a film and stuff, and see on in big sizes. And the first thing I'm going to talk about is sort of fluids. That's the area that I work in. And we have our own proprietary fluid solver at Double Negative called Squirt. And one of the main things that we tackle with Squirt and generally with simulation is that we're really looking for sort of plausible realism rather than physical accuracy. We don't really care about whether things are precisely accurate. We just want something that looks good on the big screen. And what that means really is that we want a way of solving these kind of problems that's really flexible and easy to manipulate. So we want to be able to direct these problems in ways that they wouldn't realistically go in order to solve the desires of a director or the client, basically. One of the things we've been looking at quite heavily in terms of researching our fluid solver is to do with parallelism. I mean, a fluid simulation very naturally applies to parallel techniques and parallel ways of solving things. So we've done a lot of work over the last couple of years, and I'm going to run you through some of the stuff that we've tackled, some of the problems that we've had, and why we've turned towards LLVM as a solution to some of these problems. So first of all, this is a simple smoke simulation. Now what I'm showing here is about 2 years ago we started introducing some GPU acceleration to Squirt. And by doing that, we basically found what the bottleneck was in our fluid solver and ported that algorithm onto the GPU. And as you can see here, the green and blue bars represent the amount of time spent per frame for this particular simulation in calculating the pressure projection using our new GPU Poisson solver. And over the last year or so, over 70% of our pressure projections have been accelerated using this technique. But it does have its problems. Now, by offloading computation from the CPU to the GPU, we really limit ourselves because no matter how much we do, let's say we have 50% of our work is done on the GPU and 50% on the CPU, no matter how fast we make the GPU implementation, we can only really get as quick as 2 times faster and no more than that. So we're really looking for ways of improving this. The other thing that we're looking at as well is by transferring data from the CPU to the GPU across the PCI Express bus, it's just not really able to keep up with the amount of data that you're transferring. So it's really heavily limited by a memory bandwidth. So the natural solution to this is to try and put as much work as possible onto the GPU. Ideally, you want to put everything onto the GPU and solve it there. But again, that has its own set of problems as well. First of all, GPU development tends to be quite low level. You're really carefully arranging memory. Your caching is all done manually. Everything is kind of controlled quite carefully. And what you end up finding is, as GPU development hasn't been around that long, you end up with kind of layers of sort of macros and templates and sort of huge amounts of complexity to try and do relatively simple things that you might be doing repeatedly across the code base. Now, the other issue comes to the fact that the largest GPU in terms of memory available today is 6 gigabytes. And many of our simulations require as much as 24 or 48 gigs of RAM, and we just can't fit all of that onto the GPU. So there is a certain class of problems for which we have to switch back to the CPU, and it's also very useful to be able to have a GPU and a CPU implementation running together, but we don't want to have to maintain those two code bases so that they don't diverge at any point, because that's a huge amount of work for us as developers. The other issue, of course, is that we're very much, if we were to implement our entire fluid solver on the GPU, and in particular we'd be using CUDA for that, as it's the most advanced programming language for developing GPUs, we'd be very much tying ourselves to NVIDIA hardware. So we're looking for opportunities to try and improve on that and to try and solve these kind of class of problems. And so our solution to that is what I've called the Jet language and compiler. And really we're trying to solve these three problems at once. And I'm going to run you through how the language works, how the compiler is built up, and how we've kind of gone about doing that. So first of all, the language itself is a domain-specific language designed for solving these kind of simulation problems. It's quite specific. We solve a certain set of problems, and we're not trying to solve the more general, more difficult case. Now, the language itself is quite expressive, it's very high level, and it's designed around these atomic primitives. So in contrast to a lot of common sort of research into parallelization, we're not trying to apply parallelization to a sequential code base necessarily. We're trying to take a high-level language that adapts well to work sequentially or in parallel. And that's kind of a slightly different route that we've taken. And just to demonstrate that, I'm going to show you two particular primitives that we've developed for doing this, which is the voxel primitive and the reduce primitive. And these tie in quite well with fluids. So first of all, the voxel primitive. And the red grid cell here is what I've termed the focus. That's the cell on which we're doing all of our computations. And I've introduced this new operator, this colon bracket operator, for handling indices relatively. And what that means is it's really easy to access the cell that you're working on, the neighboring cells, and it just makes things a lot easier to read for these kind of problems. And as I say, we try and solve just for the focus, and then we let the compiler take care of how to scale that up to the rest of the grid and to the rest of the voxels. We borrow quite a few ideas from functional programming to solve this. In particular, the output grid is mutable, and all of the rest of the inputs and all the rest of the parameters are immutable. And the only way of changing the output grid is by returning a new value for your particular voxel that you're doing the computation on. And I'm going to show a simple kernel here. This is a weighted blur kernel, and this is an idea about how we might perform the weighted blur operation on the entire grid. And you can hopefully see the kind of computation that we're doing per voxel and how we might go about expanding that to work in parallel. So that's one particular primitive that I'm going to talk about. The other one that's quite useful to mention is the reduce primitive. Now in this case, I'm going to use a slightly unusual example to try and demonstrate how flexible this kind of approach is, in that I'm going to run a kernel which sums up the cells that are marked interior. So I'm counting the interior cells and ignoring the Neumann and Dirichlet cells. So if we're going to do this in sequence, it would be pretty straightforward. You just go down the line and sum up the interior cells. If the cell's marked as interior, you add one to it. If not, then you don't. And then you keep going until you get to the end result. And one thing I omitted to mention is the fact that the very first operation, you need some starting point, you need somewhere to begin with. And so the green cell here is what I've called the identity, which is your starting point, your initial total before you've actually done any operations. So that's a fairly simple example of how we might tackle that problem sequentially. Now I'm going to look at the same example and how we might do that in parallel. So the first thing that we do is in the first step, we use the identity and perform the first operation on all of our cells at once. And then the subsequent operations is combining the pairs of values until we get down to our final result, just as we would have done in sequence, but a slightly different way of performing the same calculation. And anyone familiar with reductions, it's quite a common operation. Now, really what we're doing here is we're taking three particular pieces of information. We need to know the identity, we need to know the input reduction operation, and then we need to know the reduction operation subsequently. And we use these kind of kernels for handling that, and these particular inputs are how we illustrate how to compute that kind of logic. So that's a rough introduction to the language, and we have other primitives that we're working on, other primitives that we're developing as well. But that's just a couple of quite neat examples that hopefully explain very easily what it is we're trying to do. So now onto the actual compiler itself. So of course we're using LLVM for the compiler infrastructure, and we have a system of, we have reusable transformations that we perform to translate the primitives into something that will work sequentially or in parallel. And the idea being that this can be target agnostic so that we can introduce new targets to handle different ways of calculating the data. So first of all, this is the basic LLVM compiler model. And we have our own front end to JET, which parses and produces LLVM IR using a simple Bison front end. And it produces what I'm terming parallel aware IR. And what that means is that it's a valid form of the IR, but it uses declared but undefined JET intrinsics as placeholders for our translation passes to understand and to manipulate. And then from this stage, we then take this form of the IR and we then run our own system of passes over it using the LLVM optimization pass framework. And some of the passes are completely generic. Some of them are targeted to specific data layouts, and some are targeted to specific targets. And then from that, we generate the more standard form of the IR, whether it's sequential or parallel or for whatever target that we wish to use. And then we run the standard set of LLVM optimization passes over it to get the optimized form of the IR. And then from then, we then lower it using our required backend. And we're using the x86 backend and the PTX backend. And obviously an important part of this is the GPU code generation stage. So here's a quick summary of what's kind of available at the moment in terms of GPU code generation with LLVM. First of all, NVIDIA have written their own LLVM PTX backend, which I believe is part of the OpenCL compiler that they've released, but is yet to be part of the CUDA compiler. But that's proprietary software, and there's a chance that they might license that at some stage in the future. But we're using the open source version that's part of the LLVM repository, which was introduced back in September of last year. And I'm sure many of you are aware of the kind of work that's been done on that. In addition to that, there's also an experimental PTX backend for any shading language, which was probably the first work that was done in terms of trying to use LLVM to generate PTX. But that uses the C backend approach rather than the target-independent approach that we use for the open source version. And then finally, also for completeness, there's a lot of work going into using LLVM to generate AMD's version of PTX, which is AMD IL. So I'm just going to give a brief introduction to PTX itself for those of you that aren't so familiar with it. It's NVIDIA's GPU compute instruction set architecture, and it's used for OpenCL and for CUDA for generating PTX. And PTX is a kind of intermediate format. It's not the final binary that you'd actually run on the GPU. It's an intermediate stage that's designed to be easy to translate to different GPUs. And I've got a little summary here of the differences between LLVM IR and PTX. They're quite similar. They handle things in quite similar kind of ways. LLVM IR tends to be a SSA, whereas PTX, it's a little bit more complicated than that, but PTX isn't SSA by nature. And also LLVM IR uses, it has no sign for the integer types, whereas PTX does. And in addition, the register sets are slightly different. LLVM IR has a sort of virtual infinite register set, whereas PTX is technically finite. Now a quick summary of the actual open source backend. As I mentioned, it's a target-independent code gen approach. All of our instruction selection is done in table gen, and it supports PTX from 2.0 onwards and SM from 1.0 onwards. And it works with the 32-bit and 64-bit targets. So if you haven't used the PTX backend, here's a quick example of a sort of starting point. As an example of how to use it with LLC and how to use it. It's recently been integrated into Clang as well. And one of the primary authors, Justin Holowinski, there's a website up there that he's put up with some few samples. So if you're looking at getting into it, this is a good place to start, just with a few examples to get going. Right, so the current state of the backend itself, as I've mentioned, the instruction selection is all done with TableGen, and we support the arithmetic, bitwise, control flow. All of those instructions pretty much are all handled. We have support for multiple address spaces, global shared, constant texture memory, and we also have special register intrinsics for handling thread ID, block ID, that kind of thing as well. And we have preliminary function call support. It's not complete yet, but it's a starting point, as well as support for various thread synchronization as well. Now I'm going to talk a little bit more about the sort of register usage. We've done quite a lot of investigation into how best to reuse registers. I think this is one of the trickiest problems to solve in terms of going from LLVM IR to PTX. Because when we're working on the GPU, we don't so much have a fixed register set. We have a fixed register set per thread block. So depending on how many threads we're running with depends on how we wish to split up the registers. And if we have too few registers, then we end up using memory and spilling to memory, which is the way that we handle it inside the backend as well. We have a register overflow that translates quite nicely into registers at the end of the day. But an important point to make is the fact that PTX AS is NVIDIA's optimizing assembler that generates the low-level kind of machine code that actually runs on the GPU. And that bit is entirely proprietary. As I've mentioned, PTX is an intermediate format. So without really knowing the internals of exactly what happens with PTX AS, we are guessing a little bit about how best to use registers. And some of that's been, we've kind of understood a little bit more about how that process works as we've been working on the back end. But another point I was going to make as well was the fact that we now use basically 4 specific register sets of different sizes, which helps to reduce the number of unneeded instructions copying between registers that are actually the same type. Okay, so let's talk about some of the performance considerations. Some of this is specific to GPUs itself. Divergent branching, threads on the GPU run per warp, and if any of those threads diverge at all, it means that the GPU serializes out the operations that happen one after the other, which is obviously bad for our performance, so that's something that we can avoid. And it's something that we've been looking into in terms of the backend itself and trying to sort of reorder instructions so that they all execute the same instructions rather than having conditional control flow. Another issue as well is to do with the warp occupancy, and this very much comes down to the register use as well. If we have too many registers, we can't fit them in our register pool per thread block, so we end up reducing the number of blocks that get run per thread block, which means that our warp occupancy goes down. So it's much harder to hide the latency from transferring data in and out of memory. So that's really that's where the importance of the registers comes from, really, is trying to balance the parallelism with the use of the registers. But I think there's also quite an interesting area of research that could be done amongst the sort of computation versus register reuse, because we really want to use as few registers as possible. And if we set ourselves a particular limit for how many registers that we use, it's actually more beneficial for us to start recomputing the same values rather than start spilling to local memory, which is quite slow to get data in and out of. So I think there's definitely a trade-off between holding the same values in memory and trying to recompute them rather than using up registers to do that. So currently in development in terms of the back end, I mean, it's still quite early days, but we're working on some better function call support and also support for stack frame allocation. There's also some work going into some of the PTX-specific optimizations, some of which I've touched on the last few slides, predicated instructions, for example, and also improving the support for debugging as well. We have some support for the basic instructions inside PTX to handle debugging, but we'd like to kind of expand that to using the dwarf debugging format and various other kind of directions we want to go in. I mean, really our kind of focus at the moment is to try and support the whole part of PTX. And at the moment, in terms of the JET compiler, we actually have everything that we need currently, so it supports the entire subset of instructions and functionality that we need, but we are gradually expanding the backend to try and handle some more of the cases that it doesn't currently handle. So let me just summarize in terms of the actual language and compiler itself. One of the keys, I guess, that we're really doing is separating out the logic from the implementation. We don't want to have to keep rewriting our fluid solver in different technologies and different ways of doing things. We'd rather put some of that logic into the compiler and then be able to reuse it across different projects. So it's finding a way of expressing the logic in a way that isn't at all tied to whether it's running sequentially or in parallel or even to any particular target at all. And at the moment, we're using the x86 and PDX targets work very well for us, and I'm about to show you some examples of the timings of those two. But above all, it's really just a future-proof methodology. Like it's quite a young area of research. It's quite a young subject, and there's a lot of new directions that we can take with this, and we really kind of want to leave ourselves open to as many options as possible, really. So what are the next steps with some of this work? So more primitives, I've mentioned we're adding support for various other primitives to handle different types of data and different types of operations. More targets as well. At the moment, it's really just the single-threaded CPU version and then the GPU version. We'd like to see support for sort of multi-core CPU versions as well as multi-GPU grid clusters. Whatever we can kind of think of, there's an option to try and play with different targets and stuff that we can do. I think there's also a lot of work that we can do in terms of the optimizations as well. For the moment, all of our kernels are run independently. So there's a certain amount of overhead on both the CPU and on the GPU for actually launching each small part of data. Each bit of logic happens in its own kind of process, if you like. So I think there's a lot of opportunities to start looking for ways of combining some of those primitives together at compile time and finding ways of running with those same primitives and merging them together. So I think that's quite an interesting area that I'd like to really explore and see what we can do from that end. Okay, so now I'm just going to show you some timing examples. So this is our multi-grid Poisson solver that's now part of our grid solver. And this was first published in a paper that was released last year. And we've used the paper author's open source code for this as a basis of comparison. So between the paper author's version and our own version, on the CPU there's not a huge amount of difference between them. They're largely comparable. But then on the GPU we see a massive speed up going from sort of 93 seconds down to 6 seconds. So approximately a 15x speed up using an NVIDIA Tesla C2050. And now the entire sort of solver itself, and this is roughly made up of about 80 jet kernels. And the times come down quite significantly for that as well. It's roughly scalable in about the same kind of orders of magnitude, which is really pleasing to see. So going on a sort of 200 cube domain for our sort of standard solver, as it is at the moment, takes just over 3 hours. By moving that logic onto the CPU, we get it down to sort of 2 hours, 40 minutes, and then going onto the GPU, it's down to about 12 minutes. So we're getting about a 14x speed up by using this technique, by handling it this kind of way. So that's kind of where I'm going to leave it, really, giving you a little bit of introduction to the language itself, how flexible and expressive it is, but yet still restrictive enough to allow us control to be able to adapt it for different targets. And I'll add to the list of people that know LLVM. I think if anyone here is looking for a job, I think you've got a pretty good opportunity here with so many people looking.